Very good evening to one and all. As Professor Tepasukis has introduced me, myself Dr. Birojit, Assistant Professor working in Department of Mathematics, NIT Agartala, India. So first of all, I would like to sincerely thank Professor Andrea Tepasukis for inviting me to speak at the Artificial Intelligence seminar organized by the Mathematical Institute of Serbian Academy of Sciences and Arts, National Institute of Republic of Serbia. It is truly an honor for me. Professor Tepasukis is not only an outstanding mathematician, but also she is a very humble person. I had the pleasure of meeting her, and we had a serious, exciting academic discussion during her latest visit to India, where she has attended as a keynote speaker in an international conference at Haldia, Kolkata. So at that time we had a very serious discussion about my research work, her research work. Now coming to this talk actually, my title of the talk is Convergence and Matrix Operators on Complex Uncertain Sequence Spaces, where I will be discussing about complex uncertain sequence and its different types of convergence concepts, and then how an infinite matrix acting upon a complex uncertain sequence has bounded linear operators, and several results are established. We will be discussing that. So this is the overview of my lectures. First we will be starting with the introductions of uncertainty theory, how this theory is originated, in which situation this theory is applicable, that we will be discussing. Later, fundamental ideas of uncertainty theory will be discussed, where we will be discussing different basic ideas upon which this uncertainty theory is applicable. And then the main two topics of our study, which is uncertain sequence and the uncertain series, and how these are different from real sequence, real series, we will be discussing them. And later, matrix transformation of CUS. CUS means complex uncertain sequence. How an infinite matrix acts on complex uncertain sequence, that we will be discussing. Later, we will be discussing a lot of results we have established during our research work. And since this is an conference of artificial intelligence, so how our theoretical study is applicable in artificial intelligence, that I will be discussing, and we will be finishing this talk with my concluding remarks. Now, going to the first topic, which is introduction to uncertainty theory. So before starting with the question, what is uncertainty theory, first we need to know the origin of the theory. For that, we need to know this indeterminacy cases. What is indeterminacy? Indeterminacy is such phenomena where we cannot predict the outcome of certain experiment. When I tell about certain experiment, what do you think at first? Obviously, we will be thinking about tossing of a coin. So there are two possibilities: either it will result in head, or it will be resulting in tail. So what is the probability of coming ahead when we toss a coin once? Obviously, it will be 1 by 2. And by saying that, I mentioned one theory, which is probability theory. Yes. So for those cases, we know the most famous mathematical system which deals with indeterminacy condition is probability theory. And this theory is introduced by Kolmogorov in 1934. And this probability theory is applicable in most of the cases. Suppose when distribution functions are very close to the cumulative frequencies, then law of large number holds true, and in those cases probability theory gives us the best results. Now what about the cases when there are no distribution function at all, or if we are forming this distribution function, then cumulative frequencies are not lying close to the distribution function? What about those cases? Obviously in those cases a law of large number fails. So in those cases, what to do? Obviously probability theory will not give us a better result. So to deal with this kind of indeterminacy condition, Professor Baoding Liu of Tsinghua University introduced a new type of mathematical system, which is uncertainty theory. And this theory is introduced in the year 2002. Later, for the 5 years, he developed this theory and formulated the basic structure of this theory, and presented in the 2007 a very famous book named Uncertainty Theory. And since last decade, 2 decades I can say, this theory have been applied in different branches of mathematics, like differential equation, which is called uncertain differential equation, uncertain stock market, uncertain risk analysis, uncertain reliability analysis, uncertain matrices, then uncertain set. Like we have linear programming problem, there is uncertain programming also. So this theory has been applied in different fields of mathematics, and thus this theory has been applied in sequences also. Going to the next case, uncertain measure. Uncertain measure actually the fundamental concept of uncertainty theory. Before uncertain measure, we need to know about belief degree. Actually, by uncertainty theory, we measure the belief degree of a domain expert. Now, I will give one example. So, suppose we are talking about sudden flood. So, I came to know that Professor Tepasvis will visit in the coming month. She will be visiting India again, and she will be visiting Ladakh. So, very close to Ladakh, there is a place called Uttarakhand, and also in Kashmir also. Sudden flood occurs after each 4 or 5 years. Suddenly, some because of this global warming problem, suddenly this flood occurs. So, suppose Professor Tepasvis is coming to India. Now, she wants to know what is the chances that flood will be occurring in Kashmir. So, for that, there is not so much data are available. So, probability theory will not give better result. So, in those cases, she has to invite some domain expert. Domain expert means one decision maker. Suppose one domain expert is from Kashmir. So, Professor Tepasvis is asking that domain expert, then tell me what is the chances that a flood will occur in this month. So, suppose that domain expert tells that he believes that the chances of occurring the flood is 0.6. Now, Professor Tepasvis knows me. Although I am very far away from Ladakh, I stays in northeastern state Tripura, which is very far away from Kashmir. So, Professor Tepasvis knows me, and she asked me, Dr. Birojit, tell me what is the chances that sudden flood will occur in Kashmir. I will say, okay, I get those news after 4 or 5 years. So, suppose I am giving 0.4. So, there are two domain experts. One is me, and one is a permanent civilian from Kashmir. So, we are giving two different belief degrees. So, who Professor Tepasvis will be believing more? Obviously, that person who stays in Kashmir only. So, this belief degree actually plays a very important role in uncertainty theory, and this belief degree is measured by uncertain measure. Uncertain measure is a set function. It is a set function from measurable space to real numbers. Now, this belief degree 0. What does it mean? The belief degree or uncertain measure 0 means that this domain experts completely believes this the random this event will not happen. And what is the belief degree 1 means? It means the domain experts completely believes that the event will happen. So obviously this uncertain measure minimum value is 0, maximum value is 1, and the measure lies between 0 and 1. So there is an important, very important difference between uncertain measure and the usual Lebesgue measure we know. There is a question everyone asks, what are the differences? For Lebesgue measure there is no law, there is the lower limit 0, but there is no higher limit. But for uncertain measure, the higher limit is 1. And Professor Liu also established this, that this uncertain measure follows 3-4 axioms. First one is normality axiom, second is duality axiom, third one is subadditivity axiom. It may not follow additivity axiom. There are 2-3 more axioms are there. One is monotonicity axiom, one is product axiom. This is also a very important axiom, plays a very vital role in the study of uncertainty theory. Going to the next one, uncertainty space. So, what is uncertainty space? Actually, this uncertainty space is very important to study uncertain sequences. So, what is uncertainty space? Suppose you are considering a non-empty set capital gamma, and this L be a sigma algebra defined over gamma. I am not talking about the details of sigma algebra. Everyone knows it. If you don't know that, you can go through the internet. or any other book. So gamma is a non-empty set. This L is a sigma algebra defined over the gamma, and M is the uncertainty measure I have discussed. So M is an uncertainty measure and it is defined on L actually. So we have got three things: gamma, L, and M. If we consider this triplet or algebraic structure containing gamma, L, M, this whole together is called an uncertainty space. I will be giving one very simple mathematical example. Suppose this gamma is nothing but a 2-point set, 3-point set, gamma 1, gamma 2, gamma 3. Okay. Now L is the power set of gamma, and power set we know that it is the greatest sigma algebra. So this L power set can be a sigma algebra. Okay. So we have considered this gamma as a 3-point set, gamma 1, gamma 2, gamma 3. L we need one sigma algebra. We are considering the power set as the sigma algebra. Then we need uncertain measure. Okay, uncertain measure. It is a set function. So any set for which uncertain measure will be existing. So suppose we are considering this singleton set gamma 1, and the uncertain measure of n is 0.6. So it lies between 0 and 1. We agree. Then singleton set gamma 2. So measure of gamma 2 is equal to 0.3, and measure of gamma 3 it is 0.2. Now what about the other sets? Suppose I am considering about gamma 1, gamma 2. We need okay, I will be showing this by doing some calculation in the next video. I will be discussing about this example. Okay, so which one is the gamma we have considered? This gamma is the 3-point set gamma 1, gamma 2, gamma 3, and what is our sigma algebra? Sigma algebra is the power set. And uncertain measure we have considered. Measure of the singleton set gamma 1 it is 0.6. Measure of the singleton set gamma 2 it is 0.3, and measure of the singleton set gamma 3 it is 0.2. These are given. Now the question arises that what is the measure of gamma 1, gamma 2? So what we can say, this is measure of what is gamma 1, gamma 2? If we say gamma 3 complement, so gamma 3 complement is obviously gamma 1, gamma 2. So what is that? By duality it will be 1 minus measure of gamma 3. So 1 minus measure of gamma 3 is 0.2. So 1 minus 0.2, the result is 0.8. So like you can calculate measure of gamma 1, gamma 2 is 0.8. So what is the measure of gamma 1, gamma 3? It will be 1 minus this one, gamma 2. So it will be 0.7. And measure of gamma 2, gamma 3, it will be gamma 2, gamma 3 complement of gamma 1, it will be 0.4. Some may ask that what is the measure of phi? So phi is nothing, its measure will be obviously 0. And what is the measure of whole gamma? Whole gamma. So it is the complement of phi. Complement of phi is 1 minus 0, it will be 1. So every axioms are satisfied in this case. Okay, going to the next slide.
Start.
So in the whiteboard we have understood the example of the uncertainty space. Going to the next one. The concept of uncertain variable. Now, what is uncertain variable? Already we have discussed about uncertain space. Now, uncertain variable is a measurable function xi from the uncertainty space to the set of real numbers. So obviously, this variable I am considering xi. This is a function. It will be, the domain will be the uncertainty space, and the codomain will be real number. And what is complex uncertain variable? Obviously, the domain will be uncertainty space, and codomain will be complex numbers. Okay. So first of all, I will be giving one mathematical example of uncertain variable, and then I will be discussing a real life example of uncertain variable. So coming to the mathematical example. So we need one uncertainty space because the uncertain variable are defined on uncertainty space. Okay, I am considering an uncertainty space gamma L, where gamma is, first we have considered 3-point set, now we are considering for simplicity 2-point set, gamma 1, gamma 2. L, 1 second we are considering L as a power set. Now going to uncertain measure M. I am defining uncertain measure of singleton set gamma 1 as 0.7 and uncertain measure of gamma 2 is equal to 0.3. Can you see subdividibility axiom is satisfying? Yes, subdividibility is satisfying because if you take the union of gamma 1 and gamma 2, so it becomes measure of gamma 1 gamma 2 and it is nothing but measure of capital gamma, and 0.7 plus 0.3 it is 1. So measure of whole gamma is becoming 1. So not an issue. Now this uncertainty space is defined. Now from this uncertainty space we need to define a function, and this measure of a function will be called uncertain variable. Now I am considering a function xi. The domain is capital gamma. So from capital gamma I can either take gamma 1 or I can consider gamma 2. Now xi of gamma I am giving its value is 0 if gamma, this is a typographical error, this gamma is equal to gamma 1. That means when this gamma is equal to gamma 1 is equal to, remember, this value is 0. And if it is not gamma 1, that means if gamma is gamma 2, then the variable giving the value 1. So obviously the range of codomain is 0, 1 and the domain is the uncertainty space gamma 1, gamma 2. So thus we can say that this measurable function is a perfect example of an uncertain variable. Now I will be giving one real life example of uncertain variable. I have written actually for this for easy understanding. So I will read and try to make you understand. Suppose I have a box and this box contains 100 balls. 100 balls, okay? Each of which known to be either red or black. Okay, so it will be better if I take the white note. So I have got this white note. So suppose there is a box. There is a box. So here there are 100 balls. 100 balls. This information is given to you. Next information is given to you whatever the color about the balls. So suppose I am giving you only this information. Either it is red or it is black. Or the balls are black. Now we do not know actually the exact number of red balls and black balls are available. That means among these 100 balls, how many are red, how many are black? We don't know. So can we apply probability theory? Obviously no, because for getting results by using probability theory, we need to know the exact number of red ball and black ball. Now talk about belief degree. So belief degree can be evaluated by us. Look at here. There are red ball and black balls, we know that. So if I randomly take one ball, it will be, there are two possibilities only. Either it will be red ball or black ball. So what does my belief system says? Says that red ball coming belief degree is 0.5 and black ball is coming also belief degree is 0.5. But see, we cannot apply probability theory because we don't know the exact number of red balls and black balls there. Okay? So this drawing a red ball, this can be considered as a very good example of uncertain variable. So one may say that Dr. Birojit, can you give another example of uncertain variable? Yes, I can give. Next. So suppose there are 100 numbers. Now tell me, you are thinking about one number, particular number. What is the probability or what is the chance that this number is 10? For that we know the answer. Because there are 100 numbers, 10 is only once, so 1 by 100, the probability is there. Now suppose I am not telling about the total numbers. Earlier I said there are 100 numbers. Now I am telling, I don't know how many numbers are there. And I am telling about any unknown number. That means completely unknown number. Now probability theory fails. But this can be considered as uncertain variable. I am giving one more example. Suppose there is a person or student named Apurva. Okay? So this particular decision maker is thinks that Apurva is neither younger than 24 years and not older than 28 years. So in this case, the age of Apurva can be considered as an uncertain variable. Now, similarly, the height of a balloon can also be considered as an example of uncertain variable. So these are the examples of uncertain variable, and based on this uncertain variable, actually uncertain sequences are defined. Going back to the slides.
Start.
So going to the next concept, which is uncertain sequence. So for uncertain sequence, for any sequence, we need numbers or elements, sequential elements. How many elements will be there? Obviously infinite. First element, second element, third element, like this. For real sequence, each elements are real numbers. For complex sequence, each elements are complex numbers. What about uncertain sequence? We know the concept of uncertain variable just in the previous slide. So now, if we consider a sequence where all the elements are uncertain variables, then this sequence is called uncertain sequence. And if all the variables are complex uncertain variable, then the sequence is called complex uncertain sequence. Okay? Now, when we study about the sequences, the most important characteristic of a sequence is its convergence. So let's discuss about the convergence of uncertain sequence. First of all, in usual sense, and then we will be discussing about the 5 types of convergence concepts through uncertainty theory. So what does the concept of convergence of uncertain sequence in usual sense means? Suppose I am considering one uncertain sequence. Suppose it is given by zeta n. So what are the sequential terms? Zeta 1, zeta 2, and up to this. So all of these are uncertain variables, and we say this whole sequence is converging to another uncertain variable, suppose zeta. When? So after certain period or after certain elements, suppose zeta n, then all the sequential elements like zeta n plus 1, zeta n plus 2, and towards infinite, all these elements must be lying very close to zeta. This is the usual convergence says. The epsilon definition we can write like this: for any epsilon greater than 0, there exists a big natural number n such that the norm of the difference of zeta n minus zeta is very less. That means less than epsilon for all the elements which are greater than is equal to the big number n. That means if we take any gamma from the uncertainty space capital gamma, and if we apply this gamma on all these uncertain variables, so it becomes zeta n gamma, this is complex number, minus zeta gamma, this is again complex number, and usual sense you take norm or mod, you can say here, then this should be less than epsilon. This is the usual definition. This is the usual definition of convergence. Now, if this less than condition is not satisfying, that means if this is greater than is equal to epsilon. So what can I say? We can say this sequence is not convergent. Now, if we see for those cases, if we collect all those gammas for which this condition is convergence condition is not satisfying, this condition is satisfying, then if we see the uncertain measure of all such cases is equal to 0. So uncertain measure 0 means believed degree 0. Believed degree 0 means such cases are negligible. So for those cases for which the uncertain sequence is not converging, but those cases are negligible, so we can say that this is a special case, or this is interesting to see such kind of sequences. So this kind of sequences where this condition is satisfying, then we say that the sequence converging to zeta not in usual sense but in uncertain measure sense. So that is what I have discussed in the whiteboard, is convergence of uncertain measure. What I told is that for usual convergence, this norm should be less than epsilon for all n greater than is equal to n. That means if we apply gamma, then this modulus should be less than epsilon. Now it may happen that this inequality should not be satisfied. For those cases, if we see the measure, uncertain measure is 0, that means that cases are negligible in nature. So we can say this convergence concept as convergence in uncertain measure. Now going to the next type of convergence, which is convergence in mean. So in case of convergence in mean, we are not considering the limits of the variables zeta n. In usual sense, we can say zeta n is converging to zeta if limiting value of n tends to infinity zeta n. This gives zeta. Now for here, we are considering the expected value. So let me discuss something. We know that the probability of any event, the event may be uncertain or it may not be. That doesn't matter. The probability always lies between what? 0 and 1. But in case of expectation, what we do? We multiply by weights. To whom? To all the variables. And it may happen that the expected value is greater than 1. So, for the case of convergence in mean, we find the limiting value of the expected value of the norm of the differences zeta n minus zeta. And if we see that this limiting value is 0, that means we can say that this zeta n is converging to zeta in the sense of mean, that means through expected value operator, and this is called convergence in mean. Going to the next concept, which is convergence in uncertainty distribution. So in case of convergence in distribution, again we are not considering the uncertain variables zeta 1, zeta 2, zeta n. Rather, we are considering the uncertainty distribution functions. Phi n. What is phi n? Phi n is the uncertainty distribution function of zeta n, that means sequential elements, and this phi, it is nothing but the uncertainty distribution of the uncertain variable zeta, which is the limit of the sequence. So if we see that the sequence of uncertainty distribution function zeta n is converging to the uncertainty distribution phi of zeta, then we say that although the original uncertain sequence is not convergent, but their sequence of uncertainty distribution or function are convergent, then we say that the original convergent or sequence is convergent in uncertainty distribution function. So three types of uncertain convergence we have discussed. The next one is convergent almost surely. In this method, we reduce the domain of convergence. So what is the original domain? This is the uncertainty space. Whole uncertainty space is the original domain. Now it may happen that the uncertain sequence is not converging in the whole space. What is the whole space? Gamma 1, gamma 2, gamma 3, gamma 4, gamma 5, gamma 6, gamma 7, like this. Now, suppose we have a subset of the whole uncertainty space. This subset is capital lambda, and we see that the uncertainty measure of this subset is equal to 1. That means belief degree is 1. So what about the outside of this subset? So by duality axiom of uncertain measure, we can say that the uncertain measure of the excluded part, that means outside part, is 0. So 0, again we can say that in this part the sequence is converging or not converging, that doesn't matter, because uncertain measure of this outside part is 0, that means that part is negligible. So here the sequence is converging or not converging, we don't care. We care about the inside part, the subset of this which has uncertainty measure 1. And if we see that the original sequence is converging inside this subset, then this is a very good characteristic. And in this case, we say the original uncertain sequence zeta n is converging to the limit zeta in the reduced domain, and we name the convergence concept as convergence almost surely. Now there is another approach to reduce this uncertainty space to certain domain, and that method I will be discussing, and again we will be naming that convergence as convergence uniformly almost surely. Why uniformly? Because if we reduce some certain subblocks from the whole uncertainty space, then also we see that convergence condition hold, and in those cases we can call the convergence as convergent uniformly almost surely. What is the method? Let's discuss. So it may happen that the complex uncertain variables zeta 1, zeta 2 up to zeta n or is infinite. What is complex uncertain variable? Already I told, complex uncertain variable are nothing but measurable function from uncertainty space to set of complex numbers. So it may happen that all those complex uncertain variables may not be defined in some subblocks. Suppose I am taking the complex uncertain variable zeta 1, zeta 5, zeta 11. So for this particular three uncertain variable, we see that these complex uncertain variable are not defined for gamma 1 and gamma 4. So in this subblock, these three particular uncertain variable is not defined, and outside it is defined, and outside the uncertain sequence is convergent also, and this particular subblock E1, which is E1, the uncertain measure is approaches to 0, that is very close to 0. So we can say that within this subblock this part is negligible. So it doesn't matter whether inside it some uncertain variable like I said xi 1, xi 5, xi 11 are defined or is not defined, that doesn't matter. Suppose there is another subblock E2, there are some other complex uncertain variables, suppose xi 2, xi 6, xi 15, these are not defined, and outside this the uncertain sequence is convergent, and for this E2 also uncertain measure is again tending to 0. So that means this part is also negligible in this context. So like this we can find another subblock E3, another subblock E4, so we can get a collection of subblocks for which the uncertain measure is approaches to 0. But the convergence condition holds outside these subblocks uniformly. So this is also very important characteristic, and the convergence concept is given a name, and the name is convergent uniformly orthogonally. Thus we have got 5 types of convergence concepts of uncertainty theory. Okay, so going to the next one, which is matrix transformation of uncertain sequences. Now since we know the 5 types of convergence concepts, we will be particularly taking only one type of convergence concept for simplicity. Suppose we are taking convergence uniformly orthogonally concept. Okay, so matrix transformation of uncertain sequence. For that we need to know what is matrix transformation. We know that a real infinite matrix here we are taking capital A is equal to this A11, A12, A21, A22, like this. All of these are real numbers. And we are taking zeta is equal to zeta n. This is a sequence of complex uncertain variable. These are real numbers. These zeta 1, zeta 2, zeta 3 are complex uncertain variables. It means functions. Now we are applying this. We are applying this matrix, real infinite matrix, on zeta. That means this zeta n. How? Nothing but matrix multiplication. So zeta applying on gamma. So it becomes zeta 1 gamma, zeta 2 gamma, like this. And this is our real infinite matrix. If we multiply this vector by this matrix, we get this. So this is the matrix transformation of the sequence zeta with respect to the matrix capital A. This is. Now here you see one thing. Each row of the transform matrix is an infinite series. You can see this one. Each term A11 zeta 1 gamma plus A12 zeta 2 gamma, and like this. So this is an infinite series. The second one is an infinite series. Like this, all these are infinite series. That means each rows are infinite series. So for existence of the transformation, all these uncertain series, all these series, infinite series needs to be convergent. Suppose this one is not converging, diverging. So this does not exist. That means if one particular element is not existing, then whole matrix multiplication is not well defined, isn't it? So for the existence of the matrix transformation, all these infinite series needs to be convergent. Now, these series, what kind of series are these? A11, it is a real number. Zeta 1, it is a complex uncertain variable. Multiplied by a scalar, it becomes complex uncertain variable. All these terms are complex uncertain variable, and you are taking the summation of complex uncertain variables infinite times, so it becomes an uncertain series. So, for the sake of the existence of matrix transformation, these uncertain series needs to be convergent. Although this uncertainty theory is applied in so many branches of mathematics, but we have seen that this uncertain series has never been researched. So for this we have introduced the concept of complex uncertain series. So an infinite series of this where all this omega n are complex uncertain variables, then we say that this series is an infinite series. So again, complex uncertain series is coming. So what is the most important characteristic of a series? It is its convergent. So we need to define the convergence of uncertain series. Now once again I have mentioned there are 5 aspects of uncertainty theory: through measure, through mean, through distribution, again by reducing the domain almost surely, uniformly almost surely. For sequences it is already defined. So for uncertain series it needs to be defined. So we have defined convergence of uncertain series in all these aspects, 5 aspects. I am mentioning 2 here. So again uncertain series is mean. So suppose this is our uncertain series, and this Sn, what is Sn? Sn is the sequences of partial sums of this one. Okay. So usual definition of convergence. What you know that if this sequential partial sum Sn, if it is converging to some finite limit say S, then we call the uncertain series is to be convergent. Now when it is not converging, when this norm of Sn minus S is greater than or equal to epsilon. Now again if we see the measure when n tends to infinity, it is becoming 0, then we can say that this in this part these are negligible, where the uncertain series convergence is not holding. So we can say that this convergence is the convergence of uncertain series in measure actually, not mean, in measure. Okay, because since we are considering uncertain measure. Similarly, like the above one idea we have discussed, similarly we can define convergence uniformly almost surely and other thing. So now we know the concept of convergence of uncertain series. So now if all these uncertain series are convergent, suppose in all uniformly almost surely, then we can say that the matrix transformation exists. Okay, this is what is written here. Okay, so we are writing this transform matrix A zeta n as A n zeta, and it is given by this only. Okay. Now going to the important results. All of the results we have prepared here are theoretical results, and these theoretical results are applicable, very much applicable in artificial intelligence and also in other applied fields of mathematics also. But our main objective is to study the theoretical parts, because we are making the foundation of the whole theory, and these foundations may be used by applied researchers in different fields of mathematics. Okay, so what is the first one? The first result is bounded linear operator from C0 to C0. What is C0? C0 is nothing but the collection of all null sequences, null complex uncertain sequences. Null uncertain sequences, since we are considering here the convergence of uniformly almost surely, so we are denoting C0 as C0 gamma US. That means all those sequences which are null sequences in the respect of uniformly almost surely. So if we consider, suppose a sequence zeta n which is convergent uniformly almost surely, not only convergent to 0. When convergent to 0, then it is called null sequences. So if we consider all those null sequence collection which is called C0 gamma US, and we are considering a real infinite matrix A, capital A, which is AMN. Then we say that this real infinite matrix acts as a bounded linear operator from C0 to C0 itself. There is a necessary and sufficient condition. The condition is that the limiting value as n tends to infinity of the matrix element A and K is 0. And this is uniform for all K. That means if you fix this K as 1. So if we fix this K as 1, that means A11, A21, A31, we are not fixing n actually. A11, A21, A31 like this, A infinity 1, the limiting value, this should be 0. For K equal to 2, again this should be 0, like this. So uniformly for K belongs to n, this condition, if this satisfied, then we can say that in real infinite matrix, this is acts as a bounded linear operator from C0 to C0 itself. Okay, and here in this case, if we take the supremum of the row-wise summation of the modulus value of matrix elements, then this is bounded. Bounded means this is finite. So if these two conditions are satisfied, then we can say that this capital A acts as a bounded linear operator from C0 gamma US to itself. And also we have proved the converse case of this above result. That means if this condition, if this matrix capital A from C0 gamma US to C0 gamma US, if this is bounded linear operator, then again this condition is satisfied. That means this part m is equal to this is less than infinity, means finite, and also the limiting value of a and k is equal to 0. We have proved that both these results in our original research paper. If any one of you are interested, then you can communicate to me. I will share the research papers also. Going to the next concept, next results. For this, we need the concept of bounded complex uncertain sequences. Once again, this is a very important concept. This is not introduced earlier before us. So we have introduced this one. Suppose we are considering a complex uncertain sequence zeta n. This sequence will be called bounded uniformly, almost surely, if again we can find a subblocks EL, all of whose measures actually are tending to 0. Not then, the measures of this one are approaching to 0. Then, if outside of these blocks, that means gamma minus EL, in these cases, in those outside blocks, if we see the sequences are bounded, that means supremum of all zeta and gamma modulus value is less than infinite, that means it is finite, then we can say that the complex uncertain sequence is bounded uniformly, almost surely. Again, we have introduced this concept through mean also, through almost surely, through uncertain measure and uncertain distribution also. Here, since time limitation is there, so I have mentioned only one concept, which is bounded complex uncertain sequence uniformly, almost surely. So the collection of all such type of sequences we are denoting by L infinity, gamma US. Why? Because we are considering this bounded uniformly, almost surely concepts. So this is the space L infinity gamma US. This is the space of all bounded complex uncertain sequences. Now this result is based on this space actually. Now again we are considering the real infinite matrix capital A. This acts again as a bounded operator from L infinity to L infinity. That means bounded linear sequence space to bounded linear sequence space. So the necessary and sufficient condition again we need to find, and we found it to be this one, this supremum of the sequential row-wise summation A and K. This should be finite. In the earlier result, we have found two conditions. This one needs to be finite, and the limit of the sequential matrix of elements needs to be 0. But here, this condition is not required. Only this condition is enough. This one, and this is the necessary and sufficient condition. That means, if it is bounded linear operator, then this condition is satisfied. If this condition is satisfied, then it is bounded linear operator. From whom to whom? From L infinity gamma US to L infinity gamma US. Going to the next concept, which is bounded linear operator from C0 to L infinity. For the first one, we have proved for C0 to C0, the second one is L infinity to L infinity. Now what about C0 to L infinity? Again we have seen that if this condition is satisfied, then this matrix acts as a bounded linear operator from C0 to L infinity also. And we have also seen that the same infinite matrix with satisfying this condition, it is acting as a bounded operator from C to L infinity also. Now you may ask, what is C? The C0, as I already said, null complex uncertain sequence. That means those complex uncertain sequences which are converging to 0. Here, converging to 0, this restriction is not applied. In general, convergence will be enough, like convergence to uniformly almost surely. So C gamma US I am telling. Okay. So this capital A acts as a bounded linear operator from C gamma US to bounded sequence space. That means L infinity gamma US also, with this condition being satisfied. Okay, going to the next, from C0 to C, that means null sequence spaces to convergent sequence spaces. Again with this condition, we have proved that the matrix acts as a bounded linear operator. Again it is satisfying from C to C also with this condition. So these all are very important results actually. Finally, for I will be discussing two more results. One is the famous Silverman-Toeplitz theorem. This results for real sequence spaces was established by mathematician Silverman-Toeplitz. We have examined that results is valid or not in the uncertain sequence space. Since this is foundational results, so we needed to prove it in the uncertain sequence space also, and successfully we have proved the same. That means if a bounded linear operator capital A is from C gamma US to C gamma US, that means I have mentioned about this C to C. So already if it is bounded linear operator, this condition is satisfying. We have proved, like Silverman-Toeplitz did, that this linear operator from C0 gamma US to C0 gamma US is bounded, as well as it preserves the limit. That means earlier in C gamma US, if a sequence is converging to some certain limit, then after applying the matrix operator, then transformed sequence is also converting to the same limit. That calls preservation of limit. So if this preservation limit condition is satisfied, then these three conditions are also satisfied. This first condition is from this theorem, and all these other conditions are satisfied from the preservation of limit. And also the convergence, converse part is also true. That means if three conditions are satisfied, this condition is satisfied, then bounded linear operator. If these two conditions are satisfied, then limits are also preserved. The final result is Cosima-Schur theorem. This is again a foundational result, very important result. If we consider a bounded linear operator from convergent uncertain sequence space to convergent uncertain sequence space, then these two conditions are satisfied. Now, if you want to verify these two conditions with these three conditions, the first condition you see here, it is the same here. It is obviously from this result actually, it is obviously. So I am mentioning both two. Now the only difference is between this one, the second and third one. Second one is the sequence, the matrix elements a and k tends to 0 for n tends to infinity for each k. For each k, that means k is fixed here, and the row-wise summation of the matrix element is 1. Now it doesn't matter if matrix element is 1 or not. This second condition is satisfying. That means if you take any natural number p, then for this natural number p, there exists the limit. That means limit of this sequential term. Earlier it was 1 for Silverman-Toeplitz theorem. Here, if we combine these two, or not combine, exclude this one, is these two. Don't think about these two. If this condition is not satisfied, then it may not be 1. But for this, the limit of this sequence of the sum of the matrix elements row-wise is always exists. Okay, so this is proved by Cosima-Schur, and in our study also we have seen this Cosima-Schur theorem also holds true in an uncertain sequence space. One more finally, I will not discuss in details, just I will be giving you this concept actually. Absolutely p-summable complex uncertain sequences. For this, we are taking the power of the sequential elements absolute values. It is p, and this p is greater than equal to 1. And if we see, after taking the power p, and then if we take the summation, if this is finite, then we say that the sequence is called p summable, absolutely p summable. And here we are taking again the excluded blocks from ek. Measure of ek is as usual tending to 0. Then obviously we know that the concept is uniformly almost surely. So we are calling the complex uncertain sequence as uniformly almost surely absolutely p summable. This is a very big name. Huh? Okay, and here in this space the norm can be defined as usual we do in the real sequence space also. So the collection of all this space we call it LP comma US, LP space in short. And once again we have proved that this this real infinite matrix A acts as a bounded linear operator from L1 comma US to LP comma US with these two conditions. So finally I want to discuss the significance of our theoretical study to artificial intelligence. Since this is a seminar on artificial intelligence, so we need to mention how our results can be applied in artificial intelligence or applied mathematics. So since our main idea was to study the sequence convergences in an uncertainty space in different approach or in different aspects of uncertainty theory, the results we have established are purely theoretical. We don't know how it can be applied in artificial intelligence, but we contemplate that our theoretical results is very much significant. We don't know how, but we know this can be applied. So, although my work is mainly theoretical, I would like to briefly mention a possible broader perspective. In modern AI system, uncertainty theory does not always come from randomness. Sometimes it comes from incomplete knowledge or belief-based information. Uncertainty theory provides a mathematical framework for holding such type of belief degrees or uncertainty. In artificial intelligence, many processes generate sequence and apply matrix transformation similar to what we studied earlier. And so the boundedness and convergence results we proved in our study can be seen as foundational tools that may support the mathematical stability of such system. At the stage, my contribution is purely theoretical, building the structure actually. Future applied researchers can explore this connection further to the artificial intelligence. So with this, I would like to conclude my lecture, and once again I thank Professor Andrea Tepasevich for giving me this opportunity to present a lecture on my research findings in uncertain sequence space. Although in that day, because of the poor network, I could not present my whole lecture in live. So that's why I have recorded all the clips in together. Some of my PhD students like Apurva and Gaurav helped me in this process, in this technical things like setting all these things. So to all the viewers who will be watching these recorded clips in the website of Mathematical Institute of the Serbian Academy of Science and Arts and National Institute of Republic of Serbia, in the website, whenever you feel you have some doubts or some questions on this particular topic, you can approach me or communicate me to this mail ID. I am always available. Once again, thank you to the organizer of the Artificial Intelligence Seminar. You are doing a great job, and once again, thanks to Professor Andrea Tepasevich for giving me this opportunity to present myself in this seminar. Namaskar.